So in this particular one, activity 1 is really a research exercise that is with the goal of teaching students just generally about air pollution. What is air pollution? How does it affect air quality? What is the air quality like where you live? What is the air quality like in other places? And so the students in this particular activity are really doing a series of kind of online research, textbook research. And then one of the handy things in the teacher's guide is there's a section that talks where we point out, potential pitfalls or sources of error. So there's discussions around that. There's resources for teachers, and each of the activities are laid out similarly.
Tammy, I would add one thing I really like about this book is, or the guide as well, is it provides example answers. And, I really like this, like, any response is okay, or, here's the things that we're looking for. So it's really helpful, I think, to the teachers who don't know anything about this topic potentially. And so I thought that was a really useful part of this as well.
Yeah, that's a good point. So you'll see in the student pages of the teacher's guide, as Hillary pointed out, the answers have been filled in. They're not in the student workbook, obviously, but and there are, all throughout the guide, there are tips and tricks for the teachers. And if you're going to be working with the teachers, it's a good idea to sort of familiarize yourself with what the tips and tricks might be. Okay. So if we just spend a couple more seconds on activity 1, the goal of this, as I mentioned, is to get kids to think about what's in the air and look around their communities and schools at what the air quality issues might be. So for example, if there are a lot of cars idling in front of the school, they may have an issue with air pollution from idling cars. If there is a charbroiler in their cafeteria, that could be an issue. So trying to get students to become aware of what the issues are around them. Yes. All right, thanks. So yeah, the goal of activity 1 is to get the students thinking about what are different sources of air pollution in and around them. And at each school or community, the issues are different. Sometimes gaseous pollutants are an issue, sometimes particulate matter is an issue, and Hillary's going to talk more about that in a few minutes. But the basics of this activity are to learn about, what's in the air that we breathe, how does air pollution affect air quality, and then to talk about the different types of air pollutants, so gases versus particles. And then the other important part is when they do the research, they'll come back into the classroom and have a discussion about what they learned, and their teacher will help them put that information in context. And so as teachers, I think that's where people with air quality background can really help the teachers who may not have that. So this is just a little bit more on activity 1. What is the air made of? Mostly nitrogen. People think it's mostly oxygen. and again, talking about pollution is any substance in the air that can cause harm to humans or animals, and it's regulated by the EPA and other agencies like the South Coast Air Quality Management District. So at this point in the curriculum, we sort of branch off and just focus mainly on particulate matter because that's what the air beam sensor measures. There are other small sensors that measure gases and other types of pollutants, but the rest of this program is really focused on particles. And with that, I'm going to turn it over to Hillary Hafner, who's going to teach us all about particles. Did you need, oh, you have one.
Yeah, no, we're good. I'm good. Good morning, everybody. All right, I talk with my hands too much to hold that because it'll be like, I'm going to go back to my graduate school days at UCLA, which is impossibly long ago. And I did I was focusing, I'm a chemical engineer, and I was focusing on particle deposition. So how quickly do particles fall out of the air by size? And it does vary. Bigger particles and really small particles fall out faster than particles of like a micron or so. So how I did that was by taking measurements in the Sepulveda tunnel underneath LAX, and then coming out to Claremont and taking ambient samples out here, and then we would compare the size distributions between those. So I had carbon monoxide and when it was actually really measurable, and then we were looking at lead particles. So because that was not too long after lead had been removed from gasoline. So my history here in the basin goes way back, and it was really weird going into the Sepulveda tunnel, let me tell you. All right, so particles. I think you've probably all seen this graphic from EPA. I don't like it in many different ways, and I'll kind of walk through why, but particles are actually really complicated. They range in size, in composition, whether they're wet or dry or a mixture. They are very small, but they're in various sizes, and those various sizes affect people differently, or the environment. So in this graphic, basically, it's showing a piece of hair, and which is about 50 to 70 microns in diameter, and you can see, you can look at a piece of hair and you can see it, right? So it's about the size that you can see. Pretty much anything smaller than that, you're not going to be able to see it with your eyes. So then, if you look at, there's little blue balls that do not represent any particle that I know of, but those are representing PM10, so particles less than 10 microns in size. And I will tell you, there are very few particles, if any, that are a perfect sphere, and unless you've made them out of styrene, they're not going to be blue. Those represent basically dust and pollen and mold and larger particles, sort of pet dander and things like that. And then PM 2.5 are the little red dots on the PM10 because they're much smaller, 2.5 microns or less. And again, they're not red dots. So one of the things I want to do eventually is to update this graphic because it's great from a visualization and thought process, but it's not very realistic. And then if you think about sand, it's a little bit bigger than hair, so that's real fine sand, would be about 90 microns. And then I don't know very much about biology, but blood cells are about 6 to 8 microns. So this gives you some sense of the size of what we're talking about, which is you can't see these particles. You can't see PM10, you can't see PM285. You can see their impact on whether or not you can see the mountains over here, because they basically either reflect or absorb light, and so that affects visibility. So that's the kind of thing. We can see dust in general, but we can't see the individual particles. The other thing about them is, again, they can be made up of organic compounds, biological compounds, like pollen or mold, dust, and breakware from with metals and other kinds of processes. Soot is another key compound that we see, the black dust. So they're very interesting, and you can spend an entire master's degree or PhD looking at particles, like I did. All right. The other thing that's interesting about particles is how long do they stay aloft? So particles are going to be emitted into the air either primarily, we call it primary emission, so right out of a fireplace or the back of a diesel truck. That's a primary emitted particle. Other particles are formed in the atmosphere, and that's called secondary formation. So they will, through chemical reactions or condensation of a gas onto a particle, or gases condensing, we can create other particles. Okay, so and we also I think in particle analysis we call them aerosols. Because if you think about, like, if you're spraying an aerosol can, those are particles, even though it's a gas, right? But they're in the form, a particle form, because you can see them like they're little droplets or whatever. But basically, particles are going to stay in the atmosphere, depending on how high they've been emitted or carried to, and how big they are and how reactive they are. So one of the things that can happen is gravity, and so you get sedimentation, so the particle will basically settle out onto a surface. And we've all seen that when you kick up some dust and you can see it fall to the surface. You can also get condensation, where you can get water or other gases that will collect onto a particle. They get attracted to the particle, they make it heavier, they make it bigger, and so then it might sediment out as well, okay? And then coagulation is where you have lots of particles and they hit each other, stick, and again, become bigger so that they can be then removed from the atmosphere through, usually through gravity. The interesting thing about the particles, and depending on their size, and again, their chemistry, is they can stay in the air for a few minutes, for hours, for days, for weeks, depending on size and then how far aloft they are. So I was thinking about this I was just in Italy, and there was a volcanic eruption. I think Mount Etna just went, and Mount Stromboli. And so, and I also saw the Mount St. Helens big explosion, in the 80s. Those particles get lofted so high in the atmosphere, they're going to circumnavigate the globe. They're almost any size, and they're going to go all over. You hear about the Saharan dust. So that gets transported all the way to the U.S., and we can measure it in Louisiana, where it's going to affect PM 2.5 concentrations. I'm sort of stealing Hillary's forecasting stuff. They actually have to forecast those particles actually hitting and impacting ambient air, at the surface. Okay, so particles are, again, they're really complicated because they can be all over. They can be transported far. It depends on how far they get mixed up. So very, very small particles basically are removed by coagulation and condensation, and they are going to last from minutes to hours, kind of things. They don't travel very far. We're talking about ultrafine, less than 1 micron. Fine particles, so the ones that we primarily talk about, PM 2.5, because that's typically the one with the most health effects. They're usually removed by sedimentation, days to weeks. PM 2.5 is what you see coming from Saharan dust, for example. And so they can go hundreds to thousands of kilometers. And then coarse PM, PM 10 or greater, basically, again, that's going to sediment out, and it's going to be in the air minutes to hours, and only not travel very far, unless it's a big haboob like we see in the Phoenix area, where that big dust cloud will go pretty far based on monsoonal activity. So, and I don't know, do you guys, we get some dust storms here? Yes, okay. So particles are kind of cool, but they're more complicated than you think from the surface.